So the headline on this story coming out of Stanford, reading people's inner thoughts, meaning thought crimes are now officially illegal.
Yeah.
As scientists discover how to read our inner thoughts. And this one is, we got brain-computer interfaces, brain implants. My deepest, darkest private secrets are now accessible. Tell me what we got going on here.
Yeah, this is a pretty crazy story. Inner thoughts, not just outer thoughts.
Right.
Not stuff that we're saying out loud. This is stuff that, we think about and we might not want anyone to know, right? Like I'm on the freeway, I get cut off by a car, I see who it is, inner thoughts. All right, inner thoughts that I don't want anyone to know. But turns out with this new tech, people might have access to it.
Okay.
So there are some pretty big ethical dilemmas.
Obviously.
Right? But before we even get into that, let's talk about like why anybody would want to do this.
Mm-hmm.
Okay? We don't want to be like Jeff Goldblum, like you didn't think if you should, right?
Right.
Yeah. Right. So one of the real problems in neuroscience is trying to understand the brain from a functional sense, from like a causal sense of like what brain regions are doing what.
Right.
And on top of that, trying to get that understanding and try to help people with neurological disorders, with paralysis, with all sorts of like neural and cognitive impairments, right? So there are people who have severe paralysis, who develop it later on in life, things like ALS or brainstem stroke, where they're completely left without control of their body. And they have this kind of locked in syndrome, where they're like totally conscious of the world, but they can't interact with it. They can't communicate with anything. And so for something like that, you would like to have a way for them to communicate. Okay. And that's fundamentally where this study is coming from.
That's the entry point for this research study.
Yes. That's the entry point where it's like, okay, can we use all of these technologies that we have with brain-computer interfaces and try to help people that have these kinds of severe debilitating paralysis?
And what's interesting about this is many people might understand or know about BCIs primarily because of the company started by Elon Musk, Neuralink.
Yeah, Neuralink.
Which is arguably, there are other ones out there, but just in the mainstream, probably one of the more well-known like use cases.
Yeah, it's also probably the most aggressive in terms of its technology.
Fair.
Yeah.
Fair. And so it's a similar space that we're operating in, but the study was primarily starting on focusing on like the medical entry point as opposed to the Matrix where we download jujitsu.
Yeah. The point is not to try and like download your inner thoughts. The point is to try to get these people with severe paralysis and ability to communicate with the world without having to resort to like really tedious avenues. Like before, people used to use eye tracking because like sometimes if you're paralyzed from the like spinal cord down, basically, you can still have control over your eyes. So you can use those eyes as a signal for like what this person is trying. Like you can train that person to like say that, certain eye movements mean something. There's also this thing called like sip and puff switches, which are like, you have like two things, one where you sip, one where you puff. And then those are two different signals from which you can like control like two different sort of electronic thingies.
You're basically communicating binary.
Yeah. And then that binary can get translated to like
something.
higher order communication.
Yep.
But you can imagine it's like super tedious, right?
Yes.
And for somebody who maybe doesn't even have that kind of ability to like control their mouth muscles, then they're just totally out of the dark, right? So one way, like the holy grail in this sort of thing is to bypass the entire active part of this communication and just go directly into somebody thinking what they're going to say and then have it be said.
Think to action.
Or yes, think straight to action.
Right.
And that's what this thing is doing. And it's actually pretty crazy the amount of tech that's involved here. It involves like first invasive electrophysiology, meaning like in the brain you're putting in electrodes and you're listening to neurons inside the brain, not on the outside with a scalp. Okay,
so this is not headgear that you can just put on.
No, this is invasive.
You have to go.
Yeah, you got to bore a hole and you got to stick a electrode down there. Okay, and then the second is you've got this input of all of your brain signals from all the neurons that are in whatever cortex that you put the electrode in. In this case, it's the motor cortex. And then that input needs to get translated into the output communication.
Right.
And this is where they used our favorite thing, artificial intelligence.
All right, AI is back.
Yeah. In this case, it's a very specific artificial intelligence paradigm. It's really just machine learning, where they're learning from the input. How do I map from input to an output kind of vocabulary and communication?
You have an input that's in brain language, and we need to output it into action language.
Yeah, exactly. So the study goes as follows. They used 4 patients that have this kind of debilitating paralysis. And what they did was they targeted the motor cortex, and they stuck in these electrodes. Now, these electrodes can be anywhere from like 100 little tiny electrodes. So electrodes are just like tiny little pieces of silicon that are connected by wires. And when you stick it inside the brain, neurons are fundamentally electrical units of like, they're like cells that use electricity as their bread and butter. Okay. So whenever they talk to one another, they create these things called spikes, action potentials, which can be registered on your electrode as a tiny little spike. Okay. And then from that spike, these spikes last like 1 millisecond to 5 milliseconds. They're extremely, extremely short. But there's like thousands of neurons in your brain that are like talking all the time. So you can listen to all of them. And you can listen to this like aggregate activity sort of like all the neurons and where they are. Like, when you put in the electrode, there's going to be multiple electrodes along some axis. And from your computer, when you plug it in, which electrode corresponds to which. And then you have some sort of like map along this axis of like where the activity is in each time bin.
In a time series.
Right? In a time series kind of thing, you have like let's say you have 124 little silicon dots, right? Then each of those 124 silicon dots is going to register some amount of activity, and then you can chunk it up. In this case, they chunked it up into about like 10 millisecond to 20 millisecond time series. So like it's at 100 hertz, 100 data points a minute. A second, and then you get like 100 data points a second.
Yes. And
then each data point is an array of like what is the activity in each of the things. Okay. So this is really high fidelity data. Right. It's a lot of data.
The point is we're recording a wide spectrum of data points in time at a very small time interval.
Yeah.
Which means that we're not looking at TV resolution from 1990. We have 4K Ultra HD as the analogy here in terms of how robust
exactly
what the input data is that we're getting.
I mean, in this sense, like EEG, like the stuff that's on your head, that stuff's like radio compared to this 4K.
Got it.
Right? Like here you're going into the brain. When you work with like EEG and stuff that's on the brain, you've got this really annoying skull that's in the middle of everything.
I was talking to someone about this the other day randomly. Skull diffraction. Like, so when you're trying to like read, like the skull is this layer.
The skull is this massive layer of bone and fat and skin. And so, the neurons, they talk at, 1 millisecond intervals. All of that signal is going to get completely filtered out by the skull. You're not going to hear any individual neurons or even chatter at that frequency.
That makes sense.
The skull basically acts like a low pass filter. Okay. All of the high pass signal, all the higher frequency signal just gets filtered out. So you really need to go inside the brain to listen to this kind of data.
Maybe God decided it wouldn't be a great idea for people to be able to read your thoughts. If the signals were accessible inside of your head.
Well, I don't even think God like thought that we would be getting this far, right? If God was behind evolution, he was just like, okay, the brain is great. We need to make the skull real thick, because the humans have no other advantage. Right, we can't swim fast. We're not the strongest, but we got a good brain. So then, evolution was just like, all right, I'm gonna encase this thing, and we're gonna keep it safe. And then now we're so far advanced, we're like,
let's get in there. Let's mess with the secret formula a little bit.
It's pretty crazy.
But that makes sense.
So you got to really get in, and that's actually what Neuralink is doing too, right? The innovation of Neuralink is like, they were just like, no, in order to really get these kinds of brain-computer interfaces where I can think and then I'll post an Instagram story, right? I need to get inside the brain. So they bore a hole in the skull It's about the size of a nickel, and then they have like a chip that gets implanted with a bunch of electrodes that go in, and then we're listening to individual neurons from there, right? So the unfortunately, to really get into the brain, you really just got to get into the brain. Yeah,
right.
Yeah,
right.
You really got to get into the brain.
Right.
So,
you got to go to the source.
Yeah. So the way they train this thing is kind of interesting because, like, at the end of the day, okay, so now you have all this data, right? But it's just gonna be like,
right. It's effectively gibberish.
Yeah, it's just effectively just like really high frequency noise.
Right.
If you plug it into a speaker, it's gonna be like super high frequency white noise.
Okay.
Effectively, there's gonna be like little like pops, and that'll be your individual neurons. Each electrode is doing this. So you need to find a way to take all that data and put it into words.
Yep.
In English.
Yes.
Okay. In this case, English, but
could be anything.
it could be anything. So what they did was the 4 participants, they were cued on a screen to attempt speech and also imagine speech.
Okay.
So by attempt speech, I mean you don't want to say something, but you want to imagine your tongue moving and like imagine your mouth moving to say something. And then imagine speech is like the kind of imagine speech where I can just like read.
Yes.
I just read and I'm like, there's like this inner narrative
Yes.
of like what I'm reading.
If you're one of those people that doesn't have an inner voice in your head, I'm sorry.
Yeah, I guess we can't read your inner thoughts.
You can't. You're protected from the thought police.
Yeah.
But it is a fun conversation in there sometimes.
Yeah. Sometimes not what I want people to hear, but So they had the participants like choose a strategy. Okay. So either you do this motoric inner speech where you like try to sort of imagine auditory movements, and then there's like pure inner speech, which is just imagine hearing the sound, like imagine sort of reading the sound in some sense, things like that. And then so now we've got, in machine learning all the time you want the input and you want to match it to the output, and then the neural network in the middle is just going to figure it out.
Yep.
That's the magic of machine learning, right? Yep. It's like you don't actually have to tell the neural network how to figure it out because it'll do it by itself using the rules of backpropagation and this like loss that they come up with.
I get what you're saying. We have 2 sides of the equation where we have known variables.
Yeah, we have input and output.
Because you've defined what the output is by saying either of these 2
Yeah, we're like,
types.
Okay, imagine cat. They're going to imagine cat. Or they're going to imagine saying cat.
Yes.
There's going to be some neural thingy.
Yes.
And then the neural network is going to be like, okay, that neural thingy maps to cat. Right? And so and then it's going to adjust its weights in the middle to make that thing say cat.
Got it.
Right? That's how neural networks train.
Got it.
Effectively.
Yep.
So that's what they did here. And they use like a bunch of different words, and at the end of the day, so the neural network itself, it's a recurrent neural network. Okay. This is like a predecessor of the transformer model, which is now very famous in ChatGPT and all these large language models. A recurrent neural network model has this thing called a hidden state, which is effectively like a memory. Okay. And that's why these recurrent neural network models are really good at trying to sort of remember and figure out time series data.
Got it.
Okay. You can have these things called feed forward models where it's just like one layer of neurons talks to the next, talks to the next, talks to the next. This thing has a feedback loop.
Instead of being a pure linear process.
Feed forward.
Right. Feed forward.
Yeah. This thing has this back connection.
Propagation. Yep.
Yeah. Back propagation is the rule with which we set weights.
Okay.
Not to be confused with a backwards connection.
Understood.
Which is like where it's going back into its own hidden state and trying to see, okay, did this output sort of make sense with this hidden inner state? And so it's like it has this like sort of memory, you can say, where now it can keep track of temporal sequences, like time sequences, where it can keep track of the past. Right?
What's interesting about the transformer model is they had to build memory as a separate component of what we now see in like the latest ChatGPT 5 and the latest thinking models, where if you open the little drop down, you can actually see that inner dialogue.
Yeah.
But what you're I think the point you're identifying is like
that's that chain of thought type
chain
thing.
of thought.
Yeah.
That's a different thing. With the recurrent model, you get that hidden state out of the box. You don't have to sort of build.
It's like in it. Yeah. There is like a part of the neural network is a hidden state. Right. Yeah.
That makes sense. Okay. Got it. Okay. So we have we went into the brain, we wired it up with these electrodes. we have this machine learning model in the middle, and we have the output in the framework of how they define the input and output to train the model so that it could actually learn what is this high frequency noise that's coming out of the brain actually mean.
Yeah. And then the hidden, so this neural network model here, which is the recurrent neural network, it puts out like representations. Okay. And then from that, then they have a language model that takes that and then puts it into language. And that language model, you know, they've used a transformer on one of them. They've also used another type of language model. I forget the name. I think it's in here somewhere. Yeah, they've used the n-gram language model, and then they've also used a transformer language model. And the loss function that they've used is pretty interesting because it's the CTC loss function where, you know, usually when it comes to losses, so the way the loss function works is it takes its guess, and then it takes what the ground truth is, and then it computes a difference between the two, and then it's like, oh, I was really wrong here, so I really need to start changing the weights because I'm going in the wrong direction. Or it's like, oh, I'm getting closer. I'm going to keep going in this direction. That's what the loss function and backpropagation does.
Is it kind of like a scoring system?
Yeah. Effectively, it's a scoring system. That's why we call it a loss function. It's like, what is the loss between your target and your prediction, right? And then they use this thing called CTC loss, which it's kind of a loose loss function, okay? What it does is give a little bit of freedom in terms of like what the input was and what you're trying to predict. Because with the kind of data that we're working with, it's at 100 hertz, right? So it's like 1 every 10 to 20 milliseconds. But like the words that are going to come out are not going to be at that speed. So you need some bit of looseness to try to match the input to the output.
It needs room to explore a little bit.
Yeah,
it's not
exactly. In time. Yeah. Yep. And so it was like a really cool way of using like loss, but like not in this rigid format, which I thought was interesting.
That is interesting because it's maybe a little counterintuitive. Because you want rigid control over the outputs of these systems.
Yeah. Usually, if you're like if there's like a photo of a cat and you want it to be a cat, it's like, okay, no, cat is just mapped to cat, right? But this is like a sequence of stuff that we don't even know how it works. It's just like neurons talking,
and we need a little bit of discovery to allow it to have a little bit of discovery space.
Yes, yeah, in time, and that's exactly what this thing is doing. And the results are pretty interesting. So once they did this, they trained all this, and now comes the time to test. Right. Okay. So first, it's like let's just do 7 words. Okay. Like let's not do like thoughts. All right. Like why don't you think cat, and then we're gonna try to predict cat. Yeah. All right. They did that. Attempted speech was at 98% correct classification. Okay. So that's attempted speech, meaning like they thought, okay, I'm gonna say the word cat. Yes. And then the neural network was like, ooh, I see cat being represented in the neurons.
Even with grade deflation,
bro, that's an A+. That's
still an A+.
That's an A+. You know they don't have grade deflation anymore.
We're not gonna have this conversation.
No, that's for later.
Because it is very upsetting.
Because I got wrecked.
100%.
Anyways, inner speech was at 72%. Okay. So you can see that like if they think the word cat and we want to predict the word cat, that's at 98. But if they just think about the word cat, but they're not trying to like say it, right? Then it's at 72.
They're not trying to when you're not trying to trigger the motor function of speaking the word.
Yes, you got
it. It is worse. But when you add the element of the thought plus trying to trigger the motor action of moving your mouth, moving your tongue, that almost the fidelity for us to make the match is better.
Yep. Now that fidelity decreased when you went to a higher vocabulary. So like at 50%, at like a 50 word vocabulary, that fidelity decreased from 98% to like now we're getting down to like 35%. But it's still better than chance. Yes. And it's still way faster than some of the older stuff that we were doing, like eye tracking and all of these other
the pull push.
All of that stuff. I mean, this is starting out. So you can imagine like, you know, maybe more electrodes, maybe a bigger neural network with a larger hidden state, you know, more time for training, more data for training,
more individual subjects that have these in them to have a wider spectrum of different. There's a variety of very straightforward implementations.
To like make this better.
To make it better. The fundamental point is that it's possible to get to a high level of efficacy in translating the input of an inner thought to the output and knowing with a level of certainty that that's the correct translation.
That's right.
And so we have a dictionary with 7 words in it, and now
they're at 98, and now we got a dictionary of 50, and then they upgraded to a dictionary of 125,000.
Oh, interesting. Yeah.
And it was still like, way better than chance.
Yes.
It was out like 26% for inner speech, which
means they're extrapolating from the map that was built with the 7 to try to arbitrarily map to this a whole
No. They're not trying to. They built the map for each successive one.
Okay.
Yeah.
Got it.
They did build a map for each successive one.
Okay.
But it's still
no,
still
first time.
Yeah. First time's pretty damn good.
Pretty
dude.
good.
Yeah. And actually, I think they only built the map with the 50-word vocabulary, and then they tried it on this bigger one.
Yes.
And because the things sound kind of similar, like it was able to guess new novel words.
Yes.
It's pretty crazy.
That's very very interesting.
Yeah. But I think the coolest test is the following. Okay. So then they did something called the arrow recall test. Okay. This is a pretty familiar test for like psychological experiments where like you see arrows that are up, down, left, right, and things like that. And all you're doing is seeing them and then thinking about the arrow. And then this thing could say up, down.
Mm-hmm.
So even when they're not actively thinking, but they're like seeing stuff, this thing could pick up what they're like
what the
thinking
brain,
about.
Yeah, right. Like almost in this like sub rosa brain process that's happening when you're seeing something. It is even
and you're thinking about it, right?
Right.
I see an up arrow, and then this like thing is gonna up.
Oh.
And then the other thing they did was with numbers. They had like counting objects, and then the thing would put out 1, 5.
So it extrapolates beyond language.
Exactly.
To sort of like not like to like
And-
imagery.
And crucially, these two tasks are not something that the neural network was trained on.
Oh,
That's what's insane.
Yeah.
Okay? These two tasks, the neural network was trained on, these are the neurons
Yes.
that are being activated
Yes.
when this person thinks about certain words. Okay? From
Words.
that mapping, it could then take, up, like it's seeing, the guy is seeing an up arrow. The guy is counting 3 objects.
That's scary.
Right? So, like,
That's
because the
scary.
neural representations
Yes.
are going to be, like, they've abstracted
Yes.
to, like, what is the brain look like
Yes.
when it's in the space of thinking about 3,
Right.
right? Not even about trying to say 3.
Yes.
It's like
Just
the
thinking.
idea of this thing.
Yes.
What does it look like in the brain?
This
Right?
This is,
So now you can see the ethical concerns.
No. This is because very quickly. I mean, the only bottleneck to this right now is that you need brain surgery. Right.
Yeah.
Which is a high barrier.
Yeah, which
to
is its
entry.
own like ethical thing, right? Because like the only reason that these that neurosurgeons were like, okay, I'm going to do this brain surgery is because these 4 patients were like severely
Right.
paralytic, right?
Right.
And they volunteered to do this.
Right.
But like it's going to take a while for just like normal people to get
casual brain surgery.
Casual, you know?
This is very. I think what's so fascinating about this story is we all see these headlines, particularly with Neuralink being in the news, where it's like but actually understanding what's happening
Yeah.
and why it works.
It's a mechanistic like thing, right? It's like you get into the brain, you start listening to neurons, and then you start trying to decipher what those neurons are saying. How do we do that? It's by sort of training this input-output response.
and there's these underlying patterns.
And then it starts making sense. It's like, oh, that's why it works. It's not like we can just read brains.
Right.
It's like we have to learn how to read that brain.
Correct.
You know?
Correct. And that's, I think, an important detail.
Yeah.
Because it's not like I think there's 2 things that are interesting. One, there's a process by which we learn how to translate, and then also partial translation, which is like the word input output mapping they had.
Yeah.
Can also be used to, with some level of better than chance odds, make novel connections about what the brain may or may not be saying or thinking, even when you haven't mapped for those things explicitly.
Yeah.
Which means like just increasing the amount of work being done on mapping the inputs
Bro.
can have really crazy implications downstream, even if we don't map everything exactly. Which again, it's for people who work with LLMs, it's kind of very similar.
Yeah, it is. It is.
Like in that, it takes the whole corpus of the internet as text as training data, but it can still put words together in strings that are not exactly mimicking what's from the training data.
No, yeah, it's novelty now because it's learned a pattern,
Correct.
Internalized,
And,
right within its, billions and billions of parameters, right? It's learned something about it, and the next question that's obvious to ask is like, this is a slippery slope.
Yeah.
All right, what are we doing to like control this, right? Yeah. Because I mean, even if you're that paralyzed individual, maybe you don't want all your inner thought, like you're talking to someone using this interface, right? Maybe you don't want all your inner thoughts to go out, okay? All humans are kind of, fallible. No one's perfect. So how do we figure this out? And so they came up with a strategy. I don't know if it's a good one, but at least it's a strategy. It's an interesting data analysis tool. It's something called principal component analysis, PCA. It's used a lot in these kinds of like high dimensional data sets whenever you're trying to analyze them. What you're trying to do is like, you have this really high dimensional data set, but frequently if we're trying to like study like two different things, then that data is going to fall on two different directions in this high dimensional space. Okay. And that's what PCA is. It's basically trying to reduce like, what's the direction with the most information, and then what's the direction with the next most information. So they did this PCA analysis for this inner speech and attempted speech, and what they found was that when you have attempted speech and inner speech, they both fall on the same axis.
Very
It's just that the inner speech is like a little bit like sort of the amplitude along that direction is less.
Lower,
but if you have motor intent speech,
yes,
which is like, I intended to say that,
yes,
that's on a different axis. Okay, so now they can have this kind of password protection, like in their brain, where it's like the person can have some like password set that thinks along this direction, and then that opens up the BCI to be like, oh, okay, now I can like say what he's trying to think.
Right.
But and then he can go the other password, and then the BCI will shut off.
Shut off.
So you can have like this learned dimensionality in someone's brain, and then the person can like have this password in his head that he thinks about.
Yes.
And then it's like, okay, now I'm gonna.
That turns off the access to the translation.
Yeah.
We're talking.
It's a cool like way of, I don't know.
We're talking about multi-factor authentication.
Yeah, bro.
For your inner thoughts.
Yeah.
Yo,
it's like a Face ID.
Face ID in your brain.
Yeah.
Brain ID.
Yeah, dude.
#TM trademark brain ID.
Yeah.
Heard it here first. That's actually a very clever. That's a clever sort of solution to the problem that actually like lives within the control of the patient,
of the person. Yeah.
Right.
Yeah. Because at the end of the day, you like they need to be in charge.
Right.
For this thing to make any ethical sense whatsoever.
I can't believe we're talking about role-based access controls for your brain,
bro. Like, it's nuts.
This is 2025.
Yeah. I mean, there's risks, obviously, right? Like you can hack it.
Yes. Of course.
You could just, I mean, all of this is going to be in code at the end of the day, right? Where the BCI is going to choose to turn off because there's a bit of code that's like, oh, he went this way, so I'm going to turn off. You can just hack it, and then it's like neuro hacking. Now you get like into the inner thoughts.
I mean, this is literally the 3-letter agencies are going to have, neural hackers.
Yeah.
To bypass your inner thought.
Yeah, and then what started off as a medical tool
is
going to turn into something totally different. Like you could have like espionage,
100%,
surveillance,
100% counter
like
intel.
counter intel. Oof.
Yeah, no.
Yeah, interrogation.
Yeah.
Right.
I mean,
like
what do they call it?
Do I have a plead the fifth?
Yeah.
Inside my head.
Yeah. Is that the Fourth Amendment, right? Or,
yeah, I plead the fifth.
Yeah.
No, it's like it's my right to not incriminate myself.
Self-incriminate. Right.
Yeah. Right. Although I don't know, the Constitution is kind of loose today, so
this almost it's very true. I think the fourth is the right to not having a legal search and seizure, but they can just search your brain.
Yeah,
and there are so many implications.
There's so many implications, right? The founding fathers didn't know we'd be doing this bullshit.
The fact that we're talking about the constitutional implications of brain-computer interfaces is crazy that we're talking about this in 2025.
And I think it like. Papers like this really start putting an impetus on us as a society to start talking about this in a much more serious way.
Right.
Like we've had social media
Yes.
and our data online
Yes.
for 20 plus years now.
Yes.
And there's barely any legislation
Right.
in Congress trying to deal with like data privacy rights.
Which I've actually worked on, like public advocacy work to push for data privacy laws.
It's nuts, dude.
And it's
been 20 years since everyone's been on Facebook talking about random nonsense.
And it's not that controversial of an issue, and it's weirdly caught up in political dynamics of who's being censored more, which is like irrelevant to the point of data privacy. But that's the discussion has become now. We're being more censored than you in online speech.
And so now imagine like now we get into like just neural data being everywhere, right? This stuff is gonna get uploaded,
right?
Like whose right is it? Like we need legislation, but
and now you can't sue people if they lose your data currently, and so you're just kind of SOL in terms of even getting any kind of remuneration or like financial compensation.
Yeah,
I mean these are like really deep, complex issues.
Yeah, we need to start having that conversation.
It's the same. This is the same issue that the AI space is having generally, where like AI safety people or people who advocate that we need to be like thinking about AI safety have been sidelined because we're in a global arms race to reach superintelligence.
Yeah.
And stuff like this on the neural side is going to have the same game theoretic dynamics around nation states
easily
viewing the upside being more important than any of the safety allocations.
Yeah.
So this is like really, really important.
Yeah, dude.
And it might not feel like it impacts you every day, but people were talking about the social media implications 20 years ago.
Yeah.
We didn't listen to them.
No.
And now everyone's upset about the way it works.
Yeah.
And that's because we didn't listen to the people talking about this and saying that this was going to happen.
Exactly. Like 20 years ago on social media, I was just talking about like, oh, I'm going to my friend's house. And then now today we're like declaring war and like fixing elections. Like what's going to happen here?
Yeah. Yeah. The implications are crazy. And this is definitely going to be an arena. We've touched on a couple of these like neuroscience stories, and they all kind of intersect at the same nexus, which is that the research progress is moving apace. The public understanding is not keeping up with where it is.
No.
And the political will to even learn about it such that you could legislate for it is
it's
zero.
not there. Yeah.
It's zero.
Everyone's thinking about the next election in 2 years. Right. It's super annoying. But science is just moving forward and technology is moving forward because like these players, they're just trying to push.
Yep.
And then maybe Jeff Goldblum was right. Like maybe we do need to stop and think like, okay, should we be doing this? And maybe if we should, like, what are the safeguards?
Yes.
Right. How can we make sure that this isn't going to be like getting nasty?
Yeah. Because it can get nasty very quickly.
Yeah.
An incredible story out of Stanford. Thought crimes are definitely illegal now.
Yeah.
They're
about to be.
We're already seeing that with ICE. So we're on the road.
Yeah, dude.
On that depressing note, we'll do a hard pivot.
It's not totally depressing, I will say, right? Like, I mean, the prospect of like giving paralyzed individuals the ability to communicate like is pretty awesome. 100%. But at the same time,
especially for folks who either have someone in their family or in their network or their friends that are impacted by something like that, or your parents, right? As you get older, parents, naturally we all have these neurodegenerative diseases.
Yeah, I mean, like if we get someone like Stephen Hawking around today,
right,
they could be using something like this instead of like the computer interface, right?
And
so but again, we need to start having the conversation. Come on.
And the scientists who did the study were.
Mm-hmm.
And that's the point.
No, they went into this like password type thing, and they were like, and they also call for it in their paper. They're like, this is clearly going to be an issue, right? Like we're thinking about the clinical aspects of it, but clearly this is going to be an issue. So
especially geopolitically with the great power war with China. But we'll come to China in our third story.